Somewhere out past everything we have ever mapped, a machine the size of a small car is moving through a region of the universe where no human being has ever looked, no probe has ever gone before, and no scientific model has ever managed to correctly predict what actually exists there. It is not a new spacecraft. It is not a product of modern engineering. It was built before the internet existed, before home computers existed, before most of the scientists currently studying its data were even born. It runs on roughly 4 watts of power. To put that in perspective, the small light inside your refrigerator uses more electricity than that. And this machine, this ancient, tiny, underpowered relic that was only ever supposed to last 5 years, is right now sending back information about the universe that is quietly shaking the foundations of modern physics. The researchers who study its data are not using words like interesting or unexpected anymore. They are using words like astonishing, baffling, and we were wrong. This is the story of Voyager 1. And here's the part most coverage of it leaves out entirely. It is not just what Voyager 1 found out there that should give you pause. It is what that discovery quietly implies about the survival of life right here on Earth. It is what is happening to the spacecraft itself, right now in the middle of its final chapter, that almost nobody is paying attention to. And it is what is about to happen in the coming months, a moment already locked into the calendar that will mark a threshold no human civilization has ever crossed before. But to get to any of that, we have to go all the way back to the beginning, because nothing about how this mission actually unfolded matches what anyone originally planned for it. On September 5th, 1977, a rocket lifted off from Kennedy Space Center in Florida, carrying a spacecraft called Voyager 1. The mission brief was simple and modest. Swing past Jupiter, swing past Saturn, take some photographs, collect some measurements, then drift away into space and go quiet. The expected lifespan was 4 years, maybe 5. NASA planned to celebrate the mission's end sometime around 1981 or 1982. It would be a successful little trip, a nice postcard from the outer solar system, and then silence. What actually happened is one of the most extraordinary things in the history of science, and most people have no real sense of how extraordinary it actually is. Voyager 1 did not go quiet. It passed Jupiter in March of 1979 and sent back the first close-up images of that planet's surface that human eyes had ever seen. It passed Saturn in November of 1980 and kept going, accelerating as it traveled, using the gravitational pull of each planet like a slingshot to add more speed, more distance, more territory covered than any spacecraft before it. By the time the 1980s ended, Voyager 1 had already traveled farther from Earth than any object humans had ever launched into space, and it was still transmitting, still sending its thin signal across the growing void, still collecting data, still functioning on hardware that modern engineers look at today and shake their heads at in disbelief. Then, 35 years after launch, something happened that made the entire story suddenly much bigger. Voyager 1 crossed the heliopause. If that word means nothing to you yet, it is the single most important boundary in our entire cosmic neighborhood. And crossing it is the rough equivalent of stepping outside of everything our civilization has ever called home. Here is how to picture it. The sun does not just provide heat and light. It constantly releases a stream of charged particles called the solar wind. And this wind blows outward in every direction, pushing against the surrounding space and forming a giant protective bubble around our entire solar system. That bubble contains every planet, every moon, every asteroid, every comet, every spacecraft we have ever launched, and every living thing that has ever existed. The outer edge of that bubble, the point where the solar wind finally runs out of energy and gets stopped by the pressure of interstellar space pressing inward from the other side, is called the heliopause. It is the actual physical boundary of our solar system. Everything inside it is ours. Everything outside it is something else entirely. And on August 25th, 2012, Voyager 1 crossed through that boundary and came out the other side. It became the first object in human history to leave the solar system. Not a metaphor, not a technicality. The first physical thing our species has ever sent into the actual space between stars. And then it kept transmitting. Think about what that actually means. We have right now a live instrument sitting inside interstellar space, not orbiting a planet, not floating somewhere in the outer solar system, not hovering near the heliopause waiting to cross it. Actually inside the dark, cold, ancient space that lies between star systems. A space that no scientist, no telescope, no ground-based model has ever been able to directly observe from the inside. And it has been sending us data about what that space is actually like. What it is telling us is not what anyone expected. Here is where the first real twist in the story arrives. For decades before Voyager 1 got there, scientists had built detailed mathematical models describing what interstellar space should look like, not guesses. Serious, peer-reviewed, rigorously tested models built by some of the most capable physicists alive. And those models all told roughly the same story. Interstellar space, the plasma between the stars, should be relatively quiet, relatively smooth. A thin, cold, sparse environment where particles drift slowly and not much happens. A kind of cosmic waiting room between star systems. Voyager 1 walked into that waiting room and found it was actually a storm. Starting in 2017, the plasma wave instrument on board Voyager 1 began detecting something nobody expected and nobody could immediately explain. A persistent narrowband emission, a faint but constant hum in the fabric of interstellar plasma that, according to every model built to describe this environment, simply should not be there in the way it is. Not a one-time burst, not a spike in the data that could be dismissed as a glitch. A continuous signal, year after year, stretching across a distance of more than 900 million miles of interstellar space. To put that in perspective, the distance from the Earth to the Sun is roughly 93 million miles. This emission has been detected across a stretch of space 10 times longer than the distance between our own planet and our own star. Scientists studying the data in findings published in the peer-reviewed journal Nature Astronomy were clear about their conclusion. Interstellar space is not the quiet, uniform void that the models described. It is turbulent. It has structure at every scale, from distances measurable in meters all the way up to distances measured in millions of miles. It is, in a genuinely physical sense, alive with motion and complexity that was completely invisible to us before, because we had never had a single instrument sitting inside it. Now stop and sit with that for a second. Every model built to describe our universe beyond the solar system was built from the outside looking in, from a planet, using telescopes and mathematics and theory alone. And the first instrument we have ever actually placed inside interstellar space is telling us those models were missing something fundamental, that the universe beyond our solar system is more complex, more dynamic, and more structured than we had assumed. But here's the part of this that stops being abstract and starts being personal, because those discoveries about interstellar space do not stay out there. They reach back here. The same bubble that separates our solar system from this turbulent interstellar environment is the bubble that protects life on Earth. The heliopause is not just a boundary line on a scientific diagram. It functions as a shield. It deflects the most dangerous forms of cosmic radiation, the high-energy particles streaming in from distant exploded stars, before they can reach the inner solar system at full strength. If that shield were meaningfully weaker or less predictable than existing models suggest, the implications for biology on Earth would be significant. And this is exactly where the data gets uncomfortable. What Voyager 1 is telling us is that the interstellar environment pressing against that shield from the outside is more turbulent, more variable, and more energetic than any model had accounted for. We do not yet know precisely what that means for the long-term stability of the shield itself. But the fact that we now need to seriously ask the question at all represents a real shift in how we understand our own vulnerability. As a species sitting inside a bubble we barely understand the outer edge of. Now the story gets stranger still, because before we get to what Voyager 1 actually found at the boundary itself, there's a moment in recent memory worth walking through, because in 2023, Voyager 1 nearly died. For 5 straight months, the spacecraft continued transmitting a signal back to Earth. But what it was sending was gibberish, corrupted code, scrambled data that the engineers at NASA's Jet Propulsion Laboratory, after decades of experience reading everything this spacecraft had ever sent, could not decode. The instrument was still alive, the signal was still arriving, but whatever it was trying to say had become completely unreadable. For a team that had been successfully operating this mission continuously since 1977, this was unlike anything they had ever faced. The cause, once identified, was both simple and devastating. A single memory chip inside the spacecraft's flight data system had physically deteriorated after nearly 5 decades of constant exposure to cosmic radiation. One small piece of 1970s-era hardware, measuring a fraction of an inch, had developed a fault corrupting the exact section of software responsible for formatting and transmitting scientific data. No alarm had gone off. No warning had been sent ahead of time. The chip had simply quietly failed after 46 years of non-stop operation in the harshest environment a human-made object has ever been placed inside. In any ordinary engineering situation, you fix a broken component by physically going to where the component is and replacing it. In this situation, the component was 15 billion miles away, unreachable by any known form of transportation, with no repair mission possible on any time frame that would matter. The only available tools were radio signals traveling at the speed of light, and even those signals took 22 hours one way just to reach the spacecraft. 22 hours for the message to arrive, another 22 hours for any response to come back. Every single diagnostic step, every attempt to probe the problem, every test of a potential fix required a minimum wait of 44 hours to complete just one round of communication. Picture what that engineering process actually looked like from inside the control room. You look at a piece of data, you form a theory about what might be wrong, you write a set of instructions designed to test that theory, you transmit those instructions. You wait 22 hours, You receive whatever the spacecraft sends back, you analyze the response, you discover something slightly different from what you expected. You form a new theory, you write new instructions, you transmit them, you wait 22 hours again, and you repeat that cycle patiently, step by step, for months, all while carrying the knowledge that a single wrong instruction sent once across 15 billion miles of void could permanently end the mission with no possibility of recovery. The team at the Jet Propulsion Laboratory worked through this for months, carefully, methodically, under a kind of pressure most engineering situations never produce. And they succeeded. They determined that the corrupted code could not be repaired directly, but it could be relocated. The affected portion of software was split into smaller sections and stored in different places within the spacecraft's available memory, each section individually checked and rewritten to function correctly from its new location, then carefully reconnected to work together as a whole. It was, in effect, brain surgery performed remotely through a 44-hour communication delay on a machine nearly 50 years old, sitting 15 billion miles away. By mid-2024, Voyager 1 came back online and began transmitting clean, readable, complete scientific data once again. And what it immediately resumed sending back was more evidence of those persistent, unexplained plasma oscillations drifting through interstellar space. More measurements of the same turbulent structure the models had never predicted in the first place. The spacecraft that should have died in 1981 had just come back from what could have been its final silence, and it came back with more things to tell us. But none of that, not the discovery of the hum, not the near-death event, not the recovery, prepared anyone for what Voyager 1 had actually found at the exact moment it crossed the heliopause back in 2012. Because this is the part of the story that the scientific papers describe in language that stops sounding like ordinary physics and starts sounding like something else entirely. For decades, the models describing the heliopause predicted what crossing it should feel like to an instrument moving through it. The solar wind on the inside gradually thinning out, the interstellar medium on the outside gradually becoming detectable. A slow, smooth transition from one environment to the other, a gradual blending at the edges, the way a river slowly meets the sea. That is not what Voyager 1 found. At the heliopause, the particles were not thinning out calmly at all. They were moving at speeds approaching a significant fraction of the speed of light. They were slamming into one another at energies generating temperatures approaching 30,000 degrees Celsius, not inside the sun, not inside any star, but at the outer edge of our own solar system, in what was supposed to be relatively cold, sparse, transitional space. Some researchers have described this region as a wall of fire, and not as a metaphor, but as a genuine concentration of ultra-energetic charged particles forming a real physical barrier at the boundary of everything we have ever called home. And then came the magnetic discovery, which turned out to matter just as much. For decades, one of the foundational predictions about crossing the heliopause was that the magnetic field environment would change dramatically and cleanly. Inside the bubble, the sun's magnetic field. Outside the bubble, the completely separate magnetic field of the galaxy. Two distinct environments with two distinct magnetic personalities, separated sharply at the boundary between them. Voyager 1 found something completely different. The magnetic fields on both sides of the heliopause were, in ways existing theory had not predicted, actually connected. The sun's magnetic field lines, carried outward by the solar wind and compressed at the boundary, were interacting with the galactic magnetic field on the outside in a process called magnetic reconnection, where field lines from different sources rearrange themselves and release energy in the process. Read that carefully, because it's the detail that quietly changes everything else in the story. The solar system and the galaxy surrounding it are not magnetically separate. They are magnetically linked. At the boundary between everything we know and everything we have not yet explored, there is a zone where energy is actively being exchanged between our home and the wider cosmos, in ways that every model built before Voyager 1 crossed that boundary had simply failed to account for. This is not a footnote in a research paper. This is not a minor correction to existing theory. If the relationship between the solar system and the interstellar environment is more dynamic, more connected, and more energetic than the models ever described, then our understanding of how the heliosphere protects Earth over geological timescales needs to be reconsidered from the ground up. Now let's talk about what is actually happening to the spacecraft itself, because the story is not finished. It is, in fact, entering what may be its final chapter, and the timeline is tighter than most people realize. Earlier this year, NASA made a decision that nobody inside the mission wanted to make. The low-energy charged particle experiment, one of Voyager 1's scientific instruments that had been collecting data almost continuously since the spacecraft launched in 1977, was switched off. Not because it stopped working, it was still functioning fine. It was shut off because Voyager 1 is running out of power and there was no longer enough of it left to keep that instrument running. Voyager 1 gets its power from three devices called radioisotope thermoelectric generators. essentially containers of plutonium-238 that produce heat as the plutonium slowly decays, heat that is then converted into usable electricity. At launch, these generators produced around 470 watts of power. Today, nearly half a century later, they produce roughly 250 watts. They lose about 4 watts every single year, a decline that is never once reversed and never will. At some point in the early 2030s, the output will fall below the minimum level needed to run any remaining instrument at all, and Voyager 1 will go permanently silent. The team managing the spacecraft has known this was coming for years. Long ago, the scientists and engineers sat together and worked out a careful plan for exactly which instruments to shut off, and in what order, to squeeze as much scientific value as possible out of the dwindling power supply for as long as possible. Of the 10 scientific instrument packages Voyager 1 carried when it launched, 7 have already been permanently turned off. Every one of those decisions is some of the hardest a scientific team can ever make, because each instrument lost represents a set of questions that will never be answered, and there is no way to switch an instrument back on if the team later decides it was shut off too early. But here is the detail that almost nobody outside the mission team is talking about. They have not given up on buying more time. NASA engineers are currently working on an experimental power restructuring procedure, an attempt to redistribute how electricity flows across Voyager 1's remaining systems in order to extract additional capacity from components currently operating at lower efficiency than they could theoretically achieve. The idea is technically complex and carries real risk, because even small changes to how power flows through a nearly 50-year-old spacecraft, with no manual override available from 15 billion miles away, could produce unpredictable results. So the team is doing what careful engineers do. They are testing the procedure first on Voyager 2, which carries slightly more available power and sits somewhat closer to Earth, making a potential failure somewhat less catastrophic if something goes wrong. Tests on Voyager 2 were scheduled for the middle of this year. If those tests confirm the procedure is safe and effective, the same approach is planned for an attempt on Voyager 1 as soon as conditions allow. And here's the detail that makes that genuinely significant. If the procedure works, there is a real possibility that the low-energy charged particle instrument, the one that was just shut down, could be switched back on. The team is cautious. They are not making promises, but they are still trying. Because with Voyager 1, the history of assuming things were finished before they actually were has never once aged well. Now comes the moment already locked onto the calendar, the one that is already certain, the one that no human civilization has ever reached before, and that will arrive regardless of whether anyone is paying attention to it. On November 18th, 2026, in the early hours of the morning Pacific time, Voyager 1 will reach a distance of exactly 1 light day from Earth. That means it will be so far away that a signal moving at the speed of light, the fastest anything in the universe can travel, will take exactly 24 hours just to reach it. If you sent a command to Voyager 1 on a Monday morning, you would not know if it arrived until Tuesday morning, and you would not receive the spacecraft's response until Wednesday morning. 2 full days of waiting just to complete a single exchange of information. No human-made object has ever been that far from Earth, not once in the entire history of civilization. On that date, Voyager 1 will cross that threshold for the first time while it is still alive, still transmitting, still sending back data, and then it will simply keep going. Every hour, it travels roughly another 38,000 miles deeper into interstellar space. The communication delay will keep growing, the power supply will keep shrinking, and at some point in the 2030s, the last signal will finally come. But even when that happens, Voyager 1 does not stop moving. There's nothing in interstellar space capable of stopping it. No friction, no atmosphere, no gravitational pull strong enough to meaningfully alter its course. It will just keep moving silently in a straight line at roughly 38,000 miles per hour into a darkness that has no end on any human timescale. And bolted to its frame, attached to the body of this dying machine, is something that will outlast all of it. A gold-coated copper disc, carrying greetings spoken in 55 human languages, the sound of rain falling on a forest, the sound of ocean waves, the sound of human laughter. 90 minutes of music chosen from cultures across the entire span of human civilization. Diagrams explaining the basic principles of our physics and mathematics, and a map built from the positions of pulsars, designed to show whoever eventually finds it exactly where in the galaxy our planet sits. The astronomer who helped design that record described it once as a message in a bottle cast into the cosmic ocean. That description still holds. Because whoever or whatever eventually finds it, whether that is another civilization a million years from now or some form of intelligence we cannot currently imagine, the record will tell them something true, that there was a species here, that they were curious, that they reached, that they built a machine out of metal and electricity and mathematics and launched it beyond everything they had ever known, carrying the sound of their own laughter along with it. That record will still be traveling long after the sun eventually swells into a red giant and swallows the orbit of the Earth. It will still be traveling after every human city, every human archive, and every piece of stone anyone ever carved a name into has been erased by geology and time. It is arguably the single most permanent object our civilization has ever made. And it is riding on a spacecraft that currently runs on less power than the light fixture above your bathroom sink. Now come back to the science, because there is one more piece of this story that deserves to sit at the center of everything else. The persistent plasma emission Voyager 1 has been detecting since 2017 is not just an anomaly sitting quietly in a dataset. It is, according to the researchers analyzing it, the first continuous, real-time measurement of interstellar plasma density that humanity has ever obtained. Before Voyager 1 began detecting this emission, scientists could only take isolated snapshots of plasma density in interstellar space, measurements triggered by specific events like shocks produced when giant eruptions from the sun traveled all the way out to the heliopause and sent ripples through the interstellar medium. Those measurements were valuable, but scattered, something like trying to understand the weather across an entire continent by checking a single thermometer once a year in one city. What the persistent emission from Voyager 1 provides instead is something closer to a continuous feed. A running portrait of interstellar plasma as the spacecraft moves through it day after day, year after year. And what that portrait is showing us is that interstellar space is not a static, uniform background. It has texture, it has weather, it has structures built from charged particles and magnetic fields that stretch for millions of miles and interact with the outer boundary of our solar system, in ways that models built from Earth could never have detected or predicted. The space between stars is not empty. It is full, it is active, it has a physical personality that we are only now, for the first time in human history, beginning to actually read. There's a question sitting at the center of all of this that the scientific community has not yet been able to answer. The persistent emission has two possible physical explanations, and researchers working on Voyager 1's data have not yet been able to determine which one is correct. The first possibility is that the emission comes from thermally excited plasma oscillations, the natural vibration of plasma particles interacting with their surroundings. This would be a genuinely significant discovery on its own, but it would fit inside existing physical frameworks without requiring them to be torn down and rebuilt. The second possibility is that what Voyager 1 is detecting is something called quasi-thermal noise, a different physical mechanism entirely, one that carries information about plasma density and temperature in a subtly but importantly different way, and one that would require existing models of the interstellar medium to be substantially revised. Distinguishing between these two explanations requires either additional data from Voyager 1 itself, which is producing less of it every year as more instruments go dark, or an entirely new mission specifically designed to study interstellar space with instruments built precisely for this purpose and capable of the measurements needed to finally settle the question. No such mission currently exists. No such mission is currently funded. The next spacecraft capable of reaching interstellar space and crossing the heliopause, if it were funded, designed, and launched starting today, would not arrive at that boundary for at least 25 years. Which means that when Voyager 1 finally goes silent, the question it raised will still be sitting there unanswered. The map it started drawing will simply stop being updated, and the only real-time window into interstellar space our civilization has ever managed to open will close and stay closed for decades. That silence is coming. The exact date isn't fixed yet, but the direction is. Every year, the power drops a little further. Every year, more instruments go permanently offline. Every year, the team managing this mission makes harder choices about what to keep running and what to finally let go. And somewhere in the early 2030s, the last instrument will reach the minimum power threshold it needs to function. And the last signal will begin its 24-hour journey home and arrive and be recorded, and there will be nothing after it. After that, Voyager 1 will simply keep moving silently at roughly 38,000 miles per hour, carrying its golden record through the darkness, passing through regions of space that human eyes will not reach for tens of thousands of years, continuing a journey that began on a morning in September of 1977, when a group of engineers pointed a machine at the stars and pressed the launch button expecting the whole thing to last 5 years. Here is the fact sitting quietly in the middle of this entire story that is easy to miss once you get caught up in the physics and the engineering and the discoveries. Right now, the only live scientific instrument humanity has ever placed in interstellar space is nearly 50 years old. It was built using technology that predates personal computers. It is powered by less electricity than the light above a kitchen stove, and it is sending back information that is actively changing how we understand the universe and our place inside it. We have built things far larger since then. We have built things far more powerful. We have built things that cost enormously more money and involve vastly more advanced technology. None of those things have told us what Voyager 1 is telling us right now, because none of those things had the one thing Voyager 1 had. None of them had the audacity to keep going long enough to actually get there. There are questions about the universe that can only be answered from inside the universe, not from a telescope on the ground, not from a satellite in Earth orbit, not from a mission to Mars or the asteroid belt, only from a machine that has actually crossed the heliopause and entered the space between stars. We have exactly one such machine. It is old, it is dying, and it is running on 4 watts of power. And as long as it is still transmitting, the responsible thing to do is keep listening, because when it finally goes quiet, the answers to some of the most important questions we have ever asked about our place in the galaxy will go quiet along with it, at least for a generation. The signal is still coming, stretched across 15 billion miles, delayed by 22 hours of pure travel time, carrying information about a universe that is stranger, more turbulent, more connected, and more extraordinary than any model ever built from Earth managed to correctly describe. And this is the part worth carrying with you after the numbers and the dates and the science fade from memory. Every civilization that has ever looked up at the night sky has wondered what actually lies beyond it, and for the entire span of human history, the question could only ever be answered with guesswork, mathematics, and light gathered from a safe distance. For the first time, that is no longer true. We built something decades ago with less computing power than a modern calculator, and sent it out far enough to actually feel the edge of our own neighborhood and step past it. It did not need to be flawless. It did not need to last forever. It only needed to keep transmitting long enough for us to start asking better questions than the ones we started with, and it has done exactly that, over and over, for far longer than anyone building it ever expected. Nobody currently working at Mission Control will be there the day the last signal finally arrives. Some of the engineers who wrote the original code that still runs this spacecraft have already passed away, their work still quietly executing decades after they finished writing it, still deciding how a 50-year-old machine spends its final watts of power. That continuity, one generation of scientists handing an aging spacecraft off to the next, and then to the next after that, is its own kind of achievement, separate from anything the instruments have ever measured. It means the questions Voyager 1 raised will not die with the people who first heard the answers. They will be inherited, studied, and argued over by researchers who were not even born when the spacecraft crossed the heliopause. Using data gathered by a machine most of them will never work on directly, because it will likely be silent before they arrive. One machine, 4 watts. One chance to listen while it still has something left to say.